Me again, for only this session, I guess. So before we start, let me quickly remind you that our assignment 3 has been posted online and you have roughly 2 weeks to work on it. It's relatively easy, maybe slightly more difficult than some of the exercises we covered in class, but this is assignment. So you can feel free to use whatever help from the large models that you like. Well, that's fine, as long as you check and submit your own solution. Make sure to submit on time. So that's assignment 3. So today's objective, we only have one objective, which is to finish the remaining of lecture number 9 about pandas. So we're going to deal with the 2 separate Jupyter notebooks. One is called pandas, which we will continue working with. The other is called descriptive. And we will use the lecture 9 slides. Before we start, do we have any questions? Yes. Screen share, it's the desktop one, right? Let me open it. Maybe I didn't. Yeah. Let me know if it works. So for those of you who haven't downloaded, right, I need to start this. Now you should be able to see it. For those of you who have not downloaded the workbook, or you can at least get it started with installing some of the packages if it's not there. Is it working? Okay, good. Any other questions? Okay, good. So same as before, I'm going to use the online version of Jupyter Notebook as an example. Then, as we mentioned in the previous lecture, depending on which kernel we are using, right, it can be either PyDide or XPython. So if it is PyDide, you can try directly importing the package called pandas. It should work. It should work like this. But if it's XPython, let me quickly show for another time. If it's XPython, then pandas is not automatically pre-installed in the online environment. We will have to manually install. So if you have error message in either the online or offline version trying to load the pandas package, have a quick look at the first cell, which contains the comments of all 3 different scenarios. If it's offline, then you can copy paste and execute this code, or simply uncomment it and run it. So for example, for the offline, let me see, this is the offline version, and I'm trying to import pandas, but it's not there yet. So I can simply uncomment the corresponding installation code for the offline Jupyter Notebook. What's wrong here? Invalid. Let me copy paste, try to put it somewhere else. So now this works. It's a bit strange. For both the offline and online version, it may take some time to, well, XPython, the kernel will take some time to change the kernel from PyDide to XPython. So it's taking too long, it seems. Anyway, as long as one of them work, it should be fine. But here, just to consider all the possibilities. So this is the offline version. I have pandas installed already. And then I should be able to load it directly. Right, like this. And then we can continue running whatever code below that requires certain functions from this pandas package. So this is XPython, and for XPython, pandas is not automatically there. So we will need to copy paste the XPython, which is the first line of the installation code. And it will take some time, maybe 20, 30 minutes, seconds, sorry, not minutes. So this is the somewhat tricky thing about using either the online or offline, because the environment will not remember what you use. If you are using your own laptop, the offline version of Jupyter Notebook, after you install a package, you do not need to reinstall it every time, because the package will always be there. So you only need to import it every time. But here, the online version, also the CPU desktop, every time it will maybe refresh the memory and reset. So we need to do this extra step, right, like this. So in the slide, we ended somewhere around slide number 20, 24, but we will still start from the package installation page. So let's start here. To quickly remind you, once we start talking about the Pandas series. So if you think about this, the overall roadmap of lecture 9 is that now we have some fundamental understanding or basic concepts. Since we already introduced strings, we already introduced the NumPy arrays, then we can start learning about something that is more closely related to real data sets. So we will start from Pandas series in lecture 9. Then we will spend much of the time talking about the 2 different separate referencing systems. We briefly talk about it. It's quite challenging and sometimes confusing. And then from Panda series, we're going to talk about data frames, which you can take the analogy between a one-dimensional NumPy array and a two-dimensional NumPy array. And then we will talk about some useful methods and the descriptive analytical tools in pandas. So that's the roadmap. So to start with, whenever we have an individual data set, we say that each row should be individual observation and each column should be individual feature or data series. If we focus on a specific single data series, when using the pandas package, we are using a data type called pd.series as uppercase. So this series, as we said, you can think of this as similar to a one-dimensional NumPy array, because usually we are only using a single column. We're referring to a single column. Later, after we learned all the related operations applied to a single pandas array series, we are ready to deal with multiple columns, which will be a more comprehensive data set. So we say one major difference is that between the pandas series and a one-dimensional array in NumPy is that we can set user-defined labels or names. In this case, because it's a pandas series, it's a single column, we can automatically, or we can define the row names. Like in this case, we are dealing with a data set with different people's observations of their wages, educational years, so we can define the names or the so-called index by giving the corresponding people's name. So at the end of the previous lecture, we start talking about the two different referencing systems, which we say, okay, it will be a bit challenging conceptually. Because one is about the integer position-based indices, which we usually use the color green color. That is the default system, where we call or we make the reference within a pandas series or within a data frame purely by its location or by its index, whether it's row number 1, 2, 3, and so on. The other one, the pink system, is so-called the label-based indices, which are corresponding to the user-defined name, if you give it any. Right. So we started by a few very consistent examples we have seen before, which is how do we make a reference in a single pandas series if we do not have a user-given name. So in this case, we have a pandas series called wage. That's the first column of the data set. We have not given it any user-defined name, so there's no people's name like Mary and David. So in that case, the only possible way that we can make a reference is by calling the row index or the individual position of each observation. So if we call index number 2, that will be the third observation, the third row, and so on. So all the previously learned concepts in array, in strings, will still apply. For example, in terms of the slicing reference, we need a starting point, a stopping point, a step size. And the stopping point will not be included, so that in this example, the stopping point is index number 3, but number 3 will not be selected here. And finally, keep in mind that this is also what we learned in strings. We can also start counting using a negative indices. Means that we are, instead of counting forward, we're counting backward. So -1 will be the last element, and -2 will be the second last. So once you combine this positive, negative indices with slicing expressions, and potentially you can omit some of the arguments, things can get a little bit trickier. So later we will show more examples. Similarly, if you have this is another pandas series, the second column, which is working experience, because previously when we defined this pandas series, other than the index, we gave it a name, a row name. So Mary and John are the corresponding so-called labels. So in this case, we will be able to apply the pink system or the user or the label-based system. Instead of calling the individual position or the integer indices like 0, 1, 2, we can directly call the name. If the third observation is related to John, then we can directly call John's name and refer to the value, which is 2 years of working experience. Similarly, we can call n. Roughly speaking, all the previous learned rules still apply, but with only one exception, with only one difference that we will highlight. For example, we start for slicing references, it's the same logic. We specify the starting point, the stopping point, and the step size. So in the first example, we start from John, we end by default, step size default. So by default, we are selecting all the observations starting from John to the end. So we're selecting John, David, Frank, Ben. So this is what we mentioned, the biggest and probably the only difference between the two systems, the integer position-based and the label-based system. That whenever using a slicing reference, in the pink system, which is in the label-based system, the stopping point will be included instead. Because imagine if we're using integers here, integers or indices here, the stopping point is n, starting point is Mary. So from Mary to n, and the stopping point, in the previous case, we say do not include it, so we should end up with only Mary. But here, the rules are slightly different, as I highlighted here. The stopping point in the label-based system will be included. So n, as a stopping point, will be selected as well. So the quickest way to remember this rule is that, okay, since we already mentioned the name in the stopping point, well, let's include it. Otherwise, it's a little bit counterintuitive. Well, let's go for the indices. And if you are interested in selecting individual rows, potentially in different orders, for example, here we're only selecting join and end in that order. So row number 2 and row number 1, row index 2 and row index 1. We can use an inner layer of bracket and separate the corresponding either row labels or indices by comma. Right. So to quickly compare, let's switch back to the other system, the integer position-based system again, to see more examples. So whenever we have a panda series like this, it's called experience, and we have both systems available. Means that because we already gave it the row names or the row labels, Mary and John, and at the same time, we can still use the original system, the integer position-based. So if you like, instead of calling the names directly, you can still use the integer position-based. So for example, experience close bracket 3 will give us the fourth observation, which is David's value, so 44. Similarly, if it's colon 2, this goes back to the previous rule where in the integer position-based system, the endpoint or the stopping point will not be included. So stopping at 2 means that we only selected index number 0 and number 1, which will give us the first and second observation only. All the remaining exercises are more or less similar. Experience number 3, colon, will select from the third last observation, which is David, and all the remaining observations. So David, Frank, and Ben. And finally, this example is similar to the join and AND example. Whenever you use a double layer of brackets, so brackets within brackets, and specify the individual indices or individual row names that we are trying to select, then we potentially can select individual rows or observations by arranging them into different orders, basically selecting individual rows or observations and put them together. So this 2, 0, 1 actually means that we are going to display John first, then Mary, then Anne. So by doing this, you can quickly shuffle the display sequence of certain observations by putting them in a new slice of panda series. Right? So let's quickly try to summarize before we go to the Jupyter Notebook to run the code together. So as we introduced, now we have two separate systems. One is the green one, you can call it for short, the green one and the pink one. The green one, formally speaking, the position integer based. So if you have a panda series that does not have any user-defined name, like the wage, then the two systems are the same, basically. Because there's no username, we cannot call any of the observations by the name. So the only option we have is to call the observations by the indices, 0, 1, 2, 3, 4. And this can get complicated by combining, the slicing references, also the negative indices, and so on. But the real complication is that after you have user-specified names or user-specified label, now we can feel free as the coder, as the programmer, feel free to use either of the referencing system, the green one or the pink one. The pink one, formally we can call it the label-based system, will give us the ability to make the reference by the row names that we define. So we can either call join or using any slicing operations. The only difference, as we say, the only difference is that whenever you are using a slicing reference, starting point, stopping point, step size, the stopping point in a label-based referencing system should be included. So now you may be confused a little bit, but no worries. After go through the exercise in Jupyter Notebook, I will introduce some solutions by Python that help us better identify or clarify, distinguish those two systems. But let's try running the code together first. So let's go to, I will use the online version just to illustrate, and let's try to run the code together and see if we have any issues. So far, I hope everyone is able to load or import the pandas package already. Then we start by defining our very first column, a single column of the dataset, which is using pd.series. Remember the series, the S is uppercase. So by default, it's displayed as a column. So this is one minor difference between a panda series and a one-dimensional NumPy array, because by default, pandas will think, okay, if you are only using a single series, it's a single column of a dataset. But a one-dimensional array, you can think of this as a row. So slight difference. So the major difference, the new element in the panda series that we mentioned is that other than the values, which are the numerical, the numbers, or it doesn't have to be numerical, the actual observed values in the series, we can also define the indices. By default, the index are just the integers. This is by default, also what we have been using, right? We start counting from 0, and we stop at 6, which is not included. So in the end, we will have 0, 1, 2, 3, 4, 5. So if we do not give it any user-defined name, this is the system that we need to use, 0, 1, 2, 3, 4, 5. Call them by positions or call them by integer based. However, pandas will allow us to give user-defined names. So whenever we create a new panda series, for example, this experience panda series, we can give user-specified names like people's corresponding name, like Mary and like what we have seen in the slides. So here, one potential confusion is this assignment of index, because we say something about index equal to index, which, well, might seem less clear. So let's run the code first. And this is what we have, Mary and John. Instead of 0, 1, 2, 3, 4, which is the green system that we can still use, now we have the flexibility of making the reference in either of the system. So to avoid certain confusion, when you define the name of the list, let's take a look at the type of the index. This is the sequence of names, the labels, it's a list. So we have a list of names that we define, and later it will be assigned to the row names of the panda series. So to avoid any confusion, in principle, you can call it whatever you want, because that you are defining a new list as a variable. And the variable name, you can call it, you can call it index. So when you call it index, you are assigning index to an argument, a variable called index. But when you call it, for example, index 222, so here, can someone quickly tell me whether you should update the left name or the right name to index 222? Anyone? I see some of you maybe too shy to shout, but I see many of you know the right answer. You see where my cursor is at, right? At the right. I mean, if you really don't know, we can actually try, right? If you try left, it's obviously an error. So why is updating the right? Let's go back to the very original definition of assignment, right? Whenever we use this assignment operator, it's assigning the value of something to the right to something to the left, right? So in other words, this pandas.series, this function or this object will have an optional argument called index, which by default is nothing. It's just 0, 1, 2, 3, 4, and so on. But if we decide to give it a user-defined name, then we have to predefine this list or the list of names. Then we assign this name list to an existing argument or existing object called index within the panda series. So here, index 222 is whatever name you can call it that you later assign to another thing within panda series called index, right? So to better help you understand the concepts of assignment. Then the following are the corresponding quick exercises we already mentioned in the slides. By the way, whenever we print out several things, here, after we print out something, sometimes I will include a comma and a quote /n. Well, this, we do not have to worry too much about this. This is actually just a command for the new line, or basically hitting an enter after you print out. So we have already defined wage. Let's take a closer look. Wage is a panda series, contains of 6 observations, a single column. Because we have not yet give this wage a user-defined name, we can only call them by the green system or the integer position-based. So 2 will give us 2, and colon 3 will give us all first 3 observations, and so on. So we have seen this multiple times, both in strings, in NumPy arrays, as well as here. So the green system is something that we already learned. But, so this is wage, because wage does not have a user-defined name, the green system is the only system we can use. If we talk about the other panda series, which is experience, it has the user-defined name as well as the indices. So we may feel free to use either of the system to make the reference. Let's try the pink system, the label-based system, the new system first. So if we call John, it will give us the numerical value, the value for John. If we call n, but here is a slight difference, we use a double bracket n, it will give us that row of observation. Let me quickly talk about this difference between a single and a double bracket. A single bracket should be fairly easy to understand. We're only selecting, in a single bracket, we're only making a simple reference to an individual observation. So Python will directly give me the value. We can also check the type for those two outputs. You do not have to follow me here, but let me quickly show you. So this is the previous output. When we make a direct reference to any individual observation like John, it will only give us the value. But if this is similar, we also select a single observation, but we have an extra layer of close bracket. What difference will it make is that you can think of this as select a slice, a subset of the panda series, but it only contains a single element. So instead of giving us a numerical value, it will give us a subset which is still a panda series. So let's compare the type. Well, if you're only use a single layer of bracket, the outcome will be floating number. But if you are taking a slice or a subset, the result will still be a panda series. So sometimes it's okay if you don't fully get it or sometimes confused about this. You only need to try it a little bit and check the type if you are not sure, right? This will depend on sometimes you are only interested in using the numerical value. Sometimes you are taking a subset, so you still want to get a panda series. But anyhow, the remaining exercise should be still more or less the same. If we start from John, then we select all the observations from John. If we end with n, that's the difference we were talking about. If we use the stopping point as n, then n should always be included. So Mary and n. That's probably the only difference between the two systems. So here comes the interpretation of the double brackets. So here, when we use a double bracket, we are saying, okay, I'm selecting a subset or a slice of the panda series. In the previous example, in the subset, we only have a single observation, which is n. But here, we can feel free to choose to put in as many observations in the subset as we want, also in any order that we want, right? We put join and n after join, right? So those two are the same. So join and n will give us a subset of join and n in that order. So this is the new system that we introduced once we allow the user-specified names or labels as the row name in the panda series. Well, it turns out that we can also use the old system, which is the, for experience. If you want, you can still use the integer position based by directly calling the indices. And if you want to compare, let's quickly run the code. Experience 3, let me put experience again here for quick reference. Experience number 3, which will be, although the index are not displayed here, they are still available, 0, 1, 2, 3. So it will give us David's numerical value, which is 44. And Mary and Anne will be corresponding to the first and second observation. Because number 2 will be join, and because this is an old system, join as the stopping point will not be included. And similarly, you can count from backwards, selecting the last 3 observations, David, Frank, Ben, and eventually 2 layers of bracket 201 will select the first, and the second observation, which will be join, Mary, and Anne. Right. Notice that here, when we run the code, when we run this cell of code, Python will give us a warning messages. Right. This does not mean that the code we are running is wrong. Maybe several years or next year, maybe sometime in the future, it will be deprecated, means that it will be no longer true. But at least for now, the code will still be able to run. And also, Python is very considerate. It suggests that, okay, you should use the more formal version of something called ILOC. ILOC. What does this mean? Well, that's actually exactly the next section or the next notation that we want to introduce. So let's go back to the slides quickly. So far, I think for those of you who are relatively new, you might already be confused, right? Oh, okay, we can call by directly using the indices, or we can call directly by using the names, and also they have different rules. In the first system, the stopping point should not be included. In the second one, it should be included. Then one of the biggest concern is that as a user, how do I know which system am I using? Right? When I read someone else's code, or when I read my previously written code, how do I know whether I'm using the integer position-based system or the label-based system? Is there a way for us to differentiate the two referencing systems? Well, actually, we do. We have. Formally speaking, Python will use those two methods to help us distinguish or differentiate the two systems. And the corresponding names are called LOC and ILOC. So let's try to understand the names first. Actually, the name LOC is a short term for the word location. Location. So whenever we use location, we are referring to the pink system. In other words, the label-based system. Well, whenever we use ILOC, which is iLocation, we are using the green or the integer position-based system. Now here comes the new challenge. How do we remember the name which is which, right? Let me teach you a little trick, a simple trick that, well, sometimes when we write down the for loops like in Python, as a convention, when we are referring to indices, individual indices like index from 1, 0, 1, 2, 3, 4, 5, the most common English letter we are using for indices is I. So in a for loop, usually we write down something like for I in the list of 0, 1, 2, 3, 4. So whenever we use the English letter I, it will help us make the connection to the integer or label-based system. So we use I for integer position-based a lot. So hopefully that will help you differentiate between the log and iLog. So iLog is the one that is associated with the integer or position-based. And the term without I, which is simply location, is actually the one associated with the user-defined names. So after introduce those two methods, let's take a quick look how they can help us to distinguish the two systems, right? So here I'm giving you a pair of Python code cells, and the output they generate are exactly the same, using two different separate systems. On the top, we are using the pink system, which is the label-based system where we use log, right? So whenever we are using, as a user, whenever we see log or using log, we see, okay, now we are using, there's no ambiguity. Whenever we see log, LOC, we know that we are using the label-based system. So we should call either rows or columns by its user-defined name. So here we call n, and we need to specify the log, means that we are calling by the user-defined name. Similarly, whenever we are using iLog, ILOC as a method, we are telling Python that, okay, forget about the user-defined names, I don't care. I want to use the integer position-based, right? So n will have the integer position of index number 1. So both lines of the code are identical. Both will give us the same output. That's the first exercise. Similar to others, for example, Frank colon will give us all the observations starting from Frank and to the last observation. So whenever we use log, we call by the row name, which is Frank colon. Whenever we use ilog, we use for colon. Well, that should be consistent or exactly the same. Similarly, whenever you are using a double layer of brackets, we say, okay, we are making a selection of a subset, and it's the same. Whenever we use log, we are making reference by calling the labels, Mary, John. Whenever we use ilog, because of this extra little I, we are making reference to only the indices, or the integer position-based. So 0, 2 corresponding to Mary and John. So both lines of code will give us exactly the same output. Right? So in the last example, we changed nothing but the step size. So here, it has nothing to do with anything. Well, index, whether it's index position-based or row label-based, because we never call any of them. So those two are also the same. We only specify the step size. By default, step size is usually 1. But here, if the step size is 2, then we are taking alternative observations. The first one, the third one, the fifth one, and so on. So Mary, John, and Frank. So now, hopefully, by the help of log and ilog, we can at least know which system is which. But as I promised earlier, the two systems are very different of the stopping point, right? So here we use a simple exercise, we use a simple example to illustrate that difference, right? For example, when we have a wage panda series that we do not yet give it any user-defined name. So in that case, okay, we can use either the position-based or the label-based. In that case, the labels and the indices are identical because by default we have not assigned any user-defined names yet. So now here we make a big difference when we use any of the system, because when we use the first system, the integer position-based systems, we say the stopping point should not be included. For example, if we use this, that was ilog. And whenever we use the labels-based system, we say the stopping point should be included. So how does Python know when you are calling 0, 1, 2, which system you are using? Because Python need to decide, okay, now your stopping point is index number 2. Different systems ask me to do different things. If it's the green system, I should leave it. If it's the pink system, I should keep it. Well, that's the difference. So in this case, ilog and log are becoming particularly useful because, well, after we specify whether it's log or ilog, Python will immediately know, okay, which system we're talking about. If we're using log, that's the label-based system. Although we have not yet given it a label, so by default, the labels are identical to the indices. But at least we let Python know that, okay, now your endpoint should be included. So 0, 1, 2. We are selecting 3 observations. Stop is included, as visualized here. So if we quickly compare to ilog is totally different because by saying ilog, Python will know that we are using the integer position-based rule. And then in that set of rule, stopping point should not be included, should be excluded. So in that case, instead of the 3 observations, we're only selecting 2 of them. So through this simple exercise, we illustrate the key difference between the two systems and also the importance of specifying whether we are using log and ilog. To summarize in a single slide, log and ilog, by using log, we are talking about the label-based referencing system, and the stopping point will be included. ilog is the integer position-based system, and the stopping point should be excluded. So here is a quick coding style or coding recommendation, especially for our beginners learning Python, that whenever possible, we should specify. It is okay for us to do something like this. When you write your code, making some references, if you want to be lazy, well, that's fine. If you do not want to use any log or ilog, it's fine. It's possible that your code is still correct, but maybe it's confusing to the readers of your code and potentially to yourself as well. So as one suggestion or one recommendation in terms of the coding style, you are highly recommended to specify, to explicitly write out whether you are using log or ilog to help Python and also to help yourself to specify, okay, among the two systems, which one you are using, right? So let's quickly go to the Jupyter Notebook to run this part of the code. I think we only have a few of them, but we can compare quickly. As I promised, these 2 cells of code should generate exactly the same output, only by using 2 different systems. One is log, the label-based. The other is ilog, the integer position-based. So let's quickly try. So we have the first output of 22, 7, Mary, John, Frank. The other should give us also 22, 7, Mary, John, Frank. So that's what I meant. That's what I meant. So once we know they have the same output, let's quickly compare. N in the log system, we should call by the label name. and in the iLog system is the index of 1. So they are referring to the same thing. If you are curious what will happen in the log system or in the label-based system, instead of calling the name of n, if you directly try calling the row index, what will happen? As you imagine, well, Python will not allow this because you have already specified using log, which they should be the label-based systems, and we do not have any label of just a number of 1. So instead, we will have an error, key error, just 1. 1 is not understandable. It's not even a string of 1. It's just 1. Right? So we cannot do this. We cannot do this. And the remaining are more or less the same. Right? Frank is the index of 4. Mary and John are corresponding the index of 0 and 2. So to make a subset and to make individual selections within the subset, we will use a double layer of brackets. And the last one will take the step size of 2, which will help us select the alternative observations. And the last exercise was the one we were talking about. Well, the only difference between the two lines of code, one is log up to 2, the other is ilog. Before we even run the code, let's guess what will happen. We have already seen that in the slides. In the log system, up to 2 will include the stopping point, which is 2. So this will give us 3 observations. But for the ilog system, we say, okay, the endpoint, the stopping point, will not be included. So this will only contain 2 observations with index 0 and 1. That's the major difference. And through this exercise, hopefully you see the need, you see the necessity of why we need to specify in most cases. We need to specify whether we are using log or ilog. Otherwise, if you remove log and ilog, how will Python know, right? By default, because by default it's using the integer position base. But this may not be what you want, right? And it may create confusions. So as a recommendation, you should always specify by using log, either log or ilog, to make sure that you're only referring to the system that you need. Right, so this is about the 2 referencing systems, and potentially let's always keep in mind that the only difference between the 2 systems is that the endpoint, whether the endpoint or the stopping point will be included or not. Okay, well, do we have any questions at this point? So far in lecture 9, we have been dealing with a single column of a data set, which we call it a panda series. Whenever we have multiple panda series, then we are ready to deal with the real data sets, which is a two-dimensional. It is similar to we generalize a one-dimensional NumPy array to a two-dimensional one by both have rows and columns. So here, instead of a single column of feature, we now have a two-dimensional object in pandas, which we call it a data frame. So for those of you who are familiar with coding already, the word data frame should be quite a friend, because I personally use R a lot. In R, we also call this data frames. So let's take a closer look. How do we generalize stuff from 1D to 2D? So for a two-dimensional data set, in pandas we call it data frame. It's no longer a panda series. You can think of this consists of different columns, multiple columns. So multiple panda series will consist of a data frame. So data frame itself is an object. Here, the letters D and F are in uppercases. You can construct a new data frame in multiple ways. And in today's lecture, we are going to introduce 2 different ways. If your data set is relatively small, like in this screenshot, you can consider directly converting an exist, for example, dictionary to a new data frame. So we didn't explicitly talk about the object type called dictionary, and we may not need to do so. But in short, a dictionary is something like this. It is a list of different objects, and within, for each object, it potentially can have a sequence of values. This is the data we have, like wages. We have 5 series. We have 5 features: wage, education, experience, gender, and married. Just like what we have in Excel data file, potentially different series can have different data types. So the function that we'll be using to convert any data file, in this case, in this example, it's a dictionary, into a data frame that we can work using pandas function, the function name is just called data frame. But remember, the D and F are in uppercases. So this function, pd.dataFrame, is called a constructor. It will convert whatever the data format in some other cases, like in this case, it's a dictionary, into a new object called data frame. So if we quickly compare the data format, the object type, before and after this conversion, before it's a DICT, means dictionary, which we do not spend more time diving into details with it. But after the conversion, it becomes a new object type, which is a data frame. So what is special about this data frame that people like? You can think, in many ways, you can think of this as very similar to an Excel table, right? So it has columns, the column labels. In this case, we already have the column labels defined: the wage, education, experience, gender, and married. This is called column index. And you can check the column index by the method called columns. Also, we allow them to have the row names. In other words, the row labels or the row indices. Here, by default, we do not give it user-defined names yet. So if we do not give it user-defined names, by default, the row indices will be just integers, 0, 1, 2, 3, 4, 5. So this will bring us back to the two different systems we just learned, right? The green system and the pink system. If you have user-defined names, you can call the labels. If you don't, well, then you should use the row index. And the individual columns in the data frames are just the panda series we learned before. In the first half of lecture 9, we just learned how to define a new one and how to make certain references within a single panda series. Now that we have multiple panda series and we put them column by column, that will be a data frame. That will be a data frame. So if you are not happy with the data frame that, the row indices are integers, 0, 1, 2, 3, 4, that's not very informative. We do not like it. Then, same as what we did in the panda series by defining the user-defined labels, the row names, we can also do it here. We can also do it here. Remember the previous exercise, we define index and we assign the index equal to index. We can do the exactly same thing here. Index equal to index, where the right index is a list of names that we pre-specify. Oh, one thing we need to make sure is that the number of elements, in other words, the length of the list, the number of names should be the same as in the number of rows in the data set. Otherwise, the assignment is not straightforward. So whenever we construct a new data frame, this is optional, that we also give it a row name. So if a data frame has both the row name and the column name, we can imagine we are ready to make whatever references using either of the system that we learned already, but now with 2 dimensions. Because previously, the panda series only have a single dimension of only the row names. Now we have both the row names as well as the column names, so that, the things to do, the concepts are exactly the same. The only difference is that now we have 2 dimensions, both the rows and the columns. Right? So let's get ready to make some more references in a new data set. Same as before, when making a reference, we are using close brackets. And to start with, let me show you something special about a data frame. Whenever you, within a bracket, whenever you only call a single label, for example, wage, right? Whenever you only call a single label, a single name, by default, it's calling an individual column. So this is something special and slightly different than what we have seen in the NumPy 2-dimensional arrays. Right? Because usually when making the reference, we say, if we only specify one thing, we are only by default focusing on the first dimension. The first dimension here should be row, right? But instead, when we only call a single name, we're actually only calling the column. So this is one special thing about data frame, because the way that the data frames are constructed is column by column. So we still have the first dimension to be row, the second dimension to be column. The only difference is that whenever we call a single name, Python will check the column names first. So for example, if we directly call, quote, wage, it will give us the wage column. Even if you have a row name called wage, it will still give you the wage column. So this is one tricky thing, but relatively less important. A potential confusion for some of us. So once we select any individual column, and we check the type, and we say, now we decompose, we separate a single column within a data frame. Each single column is a panda series, which we are very, very familiar with already. Right? The panda series, we spend all the time talking about just now. Right? And of course, all the referencing techniques we have learned so far would still apply. If you only want to select a single column, you can call the column by quoting the name. If you want to select a subset of columns, for example, 2 columns, both the education and the experience, then we can also do this, right? But we need an inner layer of brackets. So we have encountered this 3 or 4 times already. The only difference here is that without specifying which dimension it is, by only calling the name, Python will first consider the column names. So that's one slight difference, but less important. Now let's continue. Because if you compare our data frames referencing against the single dimension of panda series, the majority of the knowledge or the rules will still apply. The only difference is that now we have 2 dimensions. So for example here, we start from the first system, which is the integer position-based system. Whenever we're using that system, here we mainly use a green color, then we can specify a dimension. Well, by default, if we only specify the selection in a single dimension, it will focus on the rows. So let me see it here. Here I think I use the label based. Here I use the wrong color. So this should be green and this should be pink, right? So for example, we have a data frame, which is, we have 6 rows and 5 columns, and all the rows and columns have their corresponding names. If I call something like 2:3, by the slicing expression, it means that we start from number 2, stop at index number 3, and because we are using the integer position-based system, stopping point should not be included, so we only select row index number 2. And for the second dimension, which is the column dimension, we do not specify anything. So by default, it is selecting everything. So the second row and all columns. Not second row, but row index number 2. Joins column and all joins row and all columns. So similarly, you can use the pink system. Here should be pink color. When using another system, we should make the same reference by calling the names. So David to Frank will give you the row index observation number 3 and number 4. Right? Here we do not have any column names of David and Frank, so the Python will allow you to do this, right? In the first dimension, by checking the row names. So a quick summary before we run the exercise together. These are exactly the same two systems. To avoid any confusion, let me repeat my recommendation in making the references in a data frame, because now it's even more complicated with 2 dimensions. So I highly recommend that we specify which system we are using by using either ilog or log. Specifically, whenever we are using ilog, we know that we are using the integer position-based system, so that in each dimension, we should be only using integer position-based, right? For example, 0, 1, 2, and so on. And keep in mind that the stopping point in this system will not be included. Whenever we are using log, we are going to use the label-based system, so make sure that in each dimension, we are calling the row and the columns by the user-defined name, if there are any. So to give you 2 quick examples, let's quickly compare how the selection will be different in a data frame. Because here, everything will be exactly the same, except for we have an extra dimension. Here, when we're using ilog, we know we should use integer position-based reference. So 1, 2, 3 will ignore 3, and by selecting only row index 1, 2, and column index 1, 2. So this will give us a 2x2 subset of the data frame, right? Because whenever we're using ilog, in a slicing expression, the endpoint, the stopping point, will never be included, right? So this is the difference. Integer position-based for both directions. I didn't see the difference between these two. Both are ilog. Whenever we are using log, this is totally different, because whenever we are using log, we are saying that, okay, we should use the pink system instead, so that we should call the columns and the rows by their corresponding labels or user-defined names. In this case, if we do not have a user-defined name for the rows, then we can directly call the indices. So in order to select the same area, which is the 2x2 and join education experience, this 2x2 subset of the data frame, using the log system, we need to specify the row indices to be 1 and 2. That's the difference, right? Previously, using ilog, we are writing down something like 1, 2, 3. But here, in order to select the same area, we are using 1 and 2, because in the log or label-based system, the stopping point will always be included. So when we say 1 and 2, it will select exactly 1 and 2. That's the difference, actually the only difference. And for the columns, because we have user-defined names, when you say education to experience, same as before, it will select both education and experience, while including the stopping point, which is experience. So those 2 pieces of code will generate the same output, well, slightly different row names, depending on whether we have defined them, but the indexing reference are slightly different. So here, I try to highlight the difference again. In the slicing expressions, depending on the 2 different systems, whether it's log or ilog, in ilog, stopping point not included. In log, stopping point included. Hopefully you understand the difference so far, now that we are expanding the dimension into a 2-dimensional data frame, right? And then, of course, some of the previously learned expressions still apply. For example, now we have 2 dimensions. If in any of the dimension, you write down nothing but a single colon, which basically means that you are taking the slicing expression and taking everything by default, which automatically gives us all the selecting everything. So in the first dimension, if it's a colon, we are selecting all the rows. In the second dimension, we have a 2, and here we are using ilog. So we are selecting column number 2, index number 2, which is a single column of experience, right? Similarly, if you want to select a subset that contains only the observations from join to Ben, so in this case, we are using log. So we know we should call the rows and columns by its name. So row-wise, let's see. Row-wise, we are calling from join to Ben, including Ben. So we are selecting the last 4 rows, join, David, Frank, and Ben. Column-wise, after the comma, we use a single colon, which is, again, means we're selecting all the columns in the second dimension. So we end up having a subset of the last 4 people's observations. Well, similarly, if it's the second dimension, well, if you're in your second dimension, by default, you are choosing everything, it will be okay to even ignore the second dimension and write down something like this. Because we are using a log method, Python will know that we are referring to the names, right? So this would be the major difference. So let's try to, let me see how many other exercises do we have. Let's try to work on some of the coding exercise here in, at least we should be familiar with constructing a data frame first. I think it's before the value assignment. Right. So let's go to the Jupyter notebook. And this is what we have covered so far in the lecture slides. We start by defining a dictionary, which is, in this example, your data set is relatively small, so you can manually type down all the information, including all the individual values, as well as their column names or even row names. So if that's the case, in most cases, your data set will be large and you cannot manually do this. So later, in the second half of lecture 9, we're going to introduce how do we read from existing data files. But to start with, let's construct this little small data frame to play with. So this is after the construction, this is what we have, and we can check the data type before and after the construction. One is dictionary, the other is something, quite complicated, but overall, the data type is a data frame. And optionally, if during the definition, during the construction, by default, we do not give it any row name. So if the row names are missing, it will take the indices, 0, 1, 2, 3, 4, 5. If we manually define the row names, for example, here we have 6 rows, so we need to give it 6 names. Same as before, here we have a list of 6 names, and feel free to change the name, because here index equal to index may seem a bit confusing to some of you. You can change it to index 222, 333, whatever other names, or you can, if you understand, you can keep it index, just to make sure the names are consistent. So here, what we do, we define a list of names and assign it to a new variable called index22 or whatever your name. Then we assign this name list to a new data frame's argument called index, which are the argument which is responsible to define the row names. Right? So after this kind of definition, we would have both the row names and the column names so that we are ready to make whatever references based on the 2 different systems. Okay, it's 20. Let's have a 10, maybe 20, 30 minutes break. Come back slightly after 30, and then we will continue. If you have questions, come talk to me. Okay, let's continue. Working with the workbook. So to start with, after we define or after we construct a new data frame. So this is our current data frame. The name does not matter. You can give it whatever name you like. And in short, usually we call them DF. DF stands for data frame, right? So this is our current data frame. So to start with, in the slides, I tell you that if you directly refer to an individual name, by default, it's selecting a column with that name. For example, wage, right? So one confusion you may have is that what if you have a data frame that with the same row and same column names? Then by doing this, we expect columns or rows, right? So also this is a bit ambiguous. So I directly ask Copilot to generate an example for us, right? This is the code Copilot generates. So in short, whatever we call a name directly, quote unquote label, Python will first check the column names. Because if you think about it again, a data frame consists of multiple panda series. So let's take a quick look of this example that Copilot generates, right? So we are constructing a new data frame called DF, which consists of 3 rows and 3 columns, and happens that the row names and the column names are exactly the same. So if we directly try calling the name of ABC, you can either think of this as the first column or the first row, right? So by default, actually, if you do not specify anything and directly call DF ABC, it will only select the first column. If you want to select the first row instead, you should specify that you are calling the column name so that it's row and column. Row as the first dimension and column as the second dimension, so you need to use the log method. So this is less important because typically in a data frame, we do not expect the row and column names to be the same. But in case. Also, you will not be tested on this, so don't worry. So once we have a data frame, we can call the individual columns by the column name, for example, a wage, right? Or combine the wage individual column will be the panda series we just learned. Correspondingly, if you want to select multiple columns, you need to use another inner bracket to make a new list that only consists of the corresponding columns. For example, if I want to separately select only the education and experience, those 2 columns, I need to make a name list for the columns that I will select. Right? So by doing this, I'm selecting a subset. So if you check the data type of the subset type of scales, that will be a data frame. So this is a little bit different. If we select a single column, each individual column will be a panda series. If you select multiple columns, that will be a subset of the data frame. So the type will be still a data frame, right? Just the smaller size of a data frame. This is slightly different, right? So now we can try make the selection. For example, we define a new variable called John, which is only by using the integer position-based indices from 2 to 3. What happens exactly here? We are selecting the rows to be 2 to 3. Well, 3 is the stopping point, but 3 is never included. So we are only selecting row index number 2, which is John's observation only. But this selection is a subset because 2 to 3 is still a list of only the element 2. So the resulting object John will be a subset, which is also a data frame. Similarly, if you want to select multiple observations by a slicing reference, by calling the labels directly, if you select from David to Frank, well, Frank is the stopping point because you are calling by the labels instead of integer indices. The stopping point will be included. So you end up selecting both David and Frank's observation. So that's the difference between the 2 systems. We talked about several times already. To avoid any confusions between the 2 systems, we use ilog and log, right? This is the suggestion we gave you, right? So whenever we are using ilog, we know, okay, we are using the integer position-based system in which the stopping point will not be included. So ilog 1, 2, 3, 1, 2, 3 in both dimensions will only select column row number index number 1, 2 and column index number 1, 2. So this will give us a subset of a 2 by 2 data frame. Instead, well, a data frame new. I see the difference now. So the difference between the data frame and data frame new are in the data frame new, we assign the row names. So if you, in this case, you make the same selection, but okay, with the row labels. Even with the row labels, we can still make the reference to the row and column indices as long as we specify we're using the ilog method. In contrast, whenever we use the log method, we are saying, okay, we are going to include the stopping point. In this case, 1 to 2, stopping point is 2, we're going to include 2. This is different. We're making the same selection. 2 by 2 data frame, but the specifications are quite different. Only because the rule difference, right? In the log system or in the label-based system, the endpoint will be included, so we need to specify 1 to 2. And also from education to experience. The reason that we call directly by the column name is that we already have column names. So instead of using the integer position-based system to refer to them, we have to call by the names. And here, both columns will be included. So although the selections are the same, compare this example to this one, the referencing systems and the mechanisms are Very different. Similar to before, we can also use a slicing reference system to either dimensions of either rows and columns. This part is a bit similar to what we have seen in a two-dimensional NumPy array, which, if you have a colon and a comma and a 2, we know what happens in each dimension. Row-wise, we're selecting all the rows. Column-wise, we're selecting column index number 2, which will give us a single column of number 2, which should be, number 2, experience, 22, and so on. Should be experience. Similarly, whenever you are using log, you need to call the rows by the names. So from John to Ben, because the endpoint will still be included, that's John, David, Frank, Ben, 4 observations. And column-wise, that is row-wise. Column-wise, you are using a single colon. That would be everything. So all 5 columns will be selected. To further simplify this expression, when we are using log, the second dimension, because by default we are selecting all the columns, it is okay. Python will allow us to just ignore the comma and colon in the second dimension, column-wise. Right? So this is what will we have. So the two expressions are exactly the same. So sometimes you can keep simplifying your expression. Well, as long as you make sure that they still make sense to you, that's fine. Now let's use this exercise to quickly illustrate the differences. Here we are using log, so we know we should call the name, right? But the only difference is that in this first exercise, in this line of code, we are selecting a single observation of joins. So in that case, let's take a quick look at the type of the selection. It should be a panda series, because we are selecting a single row, and we focus on that row only. That row by itself is a panda series. To make it different, if you want to select a subset, well, in this expression, the only difference is that on the top, we are selecting only joins observation using a single bracket. But in this case, we are selecting a subset of a data frame which contains only a single row. So using a double layer of bracket, we are basically telling Python that I'm making a selection of a subset of a data frame, but in this subset, it happens to only have a single observation of join. So the only difference will be, okay, the output values are the same, but the only difference would be the type. Here, the type, instead of a panda series, it should be a data frame. Right? That's the difference. It is okay if you do not fully get it. When you're writing down your own code, when you realize the data type is not consistent than what you expect, you can always try out by changing different layers of brackets. But to sum things up, to keep it short, in this example, because of the inner bracket, we are making the selection of individual rows, but it just happens to be, in this case, we're only selecting a single row of join. If you want, you can also select other observations, like, for example, n. Right? This is what we did before. If you are selecting multiple rows, you will have a subset with more observations. But this will not change the object type, which is the subset of a data frame, which is still a data frame. Right? So this is the slight difference between these two examples, a single bracket or a double layer of brackets. So let's continue with the slides and quickly go through the rest. So this is the exercise we were talking about, right? The difference between a single layer and a double layer. Now the remaining of the exercise mostly they are similar. Whenever we are using ilog, for example, here in this example, we are selecting a single column. Basically, we're selecting all the rows and a single column of number 2, which will give us a single column that will be a single panda series, right? However, if we slightly change the format by a slicing expression, 2 to 3, how do we interpret 2 to 3? Starting from 2, end at 3. But 3 will not be included, so eventually it will still be 2. So in terms of the selected area, it would be the same as in the previous example. So both are selecting column index number 2. However, because of the slicing operation, instead of only focusing on that specific column, it's selecting a subset which only contains column index number 2. So this will give us a panda series. This will give us a subset of the data frame, which is a data frame. So again, this column-wise example is exactly the same as the row-wise join example of a single layer or double layer of closed brackets. This, in general, is less important. Even if you do not get it, it's fine. If required, if you need to convert between types, you should know how to do this. So whether you end up with a panda series or with a data frame, usually it should not matter that much. Right? So let's continue. Once we learned all the methods or all the approaches to make certain references, we can locate or refer to any of the individual cells or any subset of the cells. So once we learn this, we can do the modification of values, updating the values, overwrite the values. They all mean the same thing. So for example, in this case, we are making the selection using log of 2 to 3 and education. So let's take a closer look. By using log, we know we should call by the names, and we know we should include the endpoint, stopping point. So row-wise 2 to 3, that would be index 2 and 3 included. Column-wise education, so we know it's education. So we are selecting the two values, 11 and 8. Well, if you want to make assignment, whether it's individual assignment or a group assignment, you can directly do so. A 9.0 will update both the values to 9.0, right? Similarly, you can also use ilog. Whenever we are using ilog, we say we are using the system of integer position-based referencing. So an ilog of 2 and 1 to 3, let's see, from dimension to dimension, row-wise is index number 2. Column-wise is 1, 2, 3, but in the ilog system or in the integer position-based system, stopping point will not be included. So as a result, we are only going to select column index number 1 and number 2. So we end up selecting two individual values, 9 and 2, and we can manually update the values to 1 at the same time. So this is the value assignment or value update, which is, well, direct and straightforward. Now let's talk about something more interesting. Let's talk about creating new columns in an existing data frame. So this is what we have done multiple times in Excel, right? We say in Excel, once we have a data table, it's automatic if we add in a new column. And sometimes the value of the new column will depend on the previous columns, and we call them a computed column or a computed field. In Python, in pandas, we can still do this. For example, here, to define a new column with a pre-specified value of all to be a string of none, you can write a code something like this. So data frame dot log, so that we are using a name-based. We start by a colon in the first index, in the first dimension means that we are selecting all the rows. And for the column name, we are using a column label or column name of remarks. So Python will be very clever. It will first try to find when any of the existing columns has the name of remarks. Well, it turns out that we do not. The current names does not have a label called remarks, so that Python will create a new column for us and make this assignment. So we end up with a new column called remarks, and all the individual observations are having the same name of a string called none. So in the following several exercises, we are going to, similarly to what we have already done in Excel, where we compute the values for certain computed field, we are going to repeat certain exercises in Python, which is much trickier because it's not straightforward. So for example, let's first try to make the analogy of filtering. We have learned how to do filtering in Excel, right? We just, in the drop-down list, we select the criteria. Then Excel will only show the corresponding observations for us. That's very easy. But in Python, it's a little bit trickier. What if you want to make the selection of the subset that only contains, by filtering out, only the female observations? Specifically, the genders, you only want to keep the observations with the gender to be female, not male. How should we do that? So in Python, we will do this using logical flow statements again. So specifically, the code will be something like this. So this line of code is not very easy to understand, but let me try to explain detail by detail. So we first have assignment symbol. We define a new list. We define a new list called isFemale. So what happens for the assignment is whatever happens after the assignment symbol, after the equal sign. So let's see, what is that exactly expression after the symbol, the equal sign. So we have something like data frame gender double equal to female. So that will be a sequence or a list of the Boolean statements. So to visualize this process, let me show it to you. Data frame gender, which will help us select a specific column of gender, which will contain 6 individual observations. The first 2 are female, the last 4 are male. Then, in the Boolean statement of double equal to female, it will compare each of the observation element-wise to the string of female. And it will return us a sequence or a list of 6 individual Boolean statements. So compare one by one, basically. So let me repeat the process. In the first step, so in this pink area, data frame gender, we select the whole column of female, female, male, 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 male. Then we are going to make the element-wise logical expression. The double equal sign actually will check whether they are element-wise equal or exactly the same in value to the string of female. So you can imagine the first 2 are female, so the value will be true, true. And the last 4 will be all false. So we end up, so this isFemale list of Boolean statements will be true, true, false, 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 false. This is what we get after executing this part of the code. And then you may ask, okay, after we get this list of sequence of Boolean statements, how is this useful? It turns out that we can directly use this list of Boolean statements as a filtering criteria. If the first 2 observations are true, the last 4 observations are false, we can directly use this. We can directly use this in the original data frame to only select the first 2 observations. In other words, only select observations that the females are true. So that will give us the filtered observations of only female workers. Right, so this is the logic. This is the logic. Similarly, let me give you another example. It does not have to be a Boolean statement. It can be a mathematical expression or in general, whatever logical statement we have. For example, if you want to filter out the observations whose wage are greater than 4, the hourly wages, then you can write down something, you can define a new sequence of Boolean statements is high wage, which should be defined as the data frame wage, the whole column, greater than 4. Then, same as before, it will return you a list of Boolean statements based on the value of the wages, and then we can directly apply this Boolean statement to the original data frame to make the corresponding filtered selection. To make things more complicated, if you still remember what we have learned in the logical expressions, both in Python as well as in Excel, we can combine multiple logical statements using AND, OR, and something similar. So for example, for AND, we have already learned the AND expression with combining single Boolean statements. It's just A and D. In pandas, if you want to evaluate element-wise two lists of Boolean statements, the symbol is just simple. Instead of using A and D, AND, we are using this version of AND, which is on your keyboard is Shift 7. So this symbol will represent AND. So it will element-wise evaluate the Boolean statement for a two sequence of Boolean statements. So recall that AND is very restrictive, so that only when both are true, it will return true. As long as one is false, it will give us false. So let's take a closer look to this example. We are trying to define a new sequence of Boolean statements called isWife. So this is either true or false. So what is the condition that this if isWife statement is true? So we need, it depends on the values of two other columns. So first, the gender has to be female, and then the marriage status has to be married. So only when those two columns are both true, or in other words, only when those two conditions are both satisfied, then our isWife, the new factor, will be true. So we are using the AND operator to connect the two statements, and we'll require both to be true in order to give us an overall true statement. Right. So in the previous three exercises in total, we have seen how do we define a new sequence, how do we construct a new sequence of Boolean statements based on the criteria or potentially multiple criteria that we have. Now you may wonder, how is this useful? Like I said, once we have a sequence of Boolean statements, and also the length by construction or by definition, the length will be equal to the number of rows, the number of observations, we can directly apply them into the original data frame to make the filtering. So if you think about it, following our first example of isFemale, so we have construct a new list of Boolean statements called isFemale that will give us true, and the others are false. So if we directly apply this isFemale in a bracket into the original data frame, what will happen? It will only select the corresponding true observations because they are true. It's a Boolean statement. The others are false. So the remaining observations are false. So it will not be selected. So as a result, when we combine the Boolean statements, use them as indices or references within the referencing brackets, Python will help us select all the observations with their corresponding Boolean statements to be true, so that it is equivalent as if we are doing something like filtering. Because after the selection, we know for sure that all the remaining observations must have the gender of female. Otherwise, it will not have the Boolean statements of true at the first place, right? So by doing this, we will have a subset of the data frame with only the female observations. So this is how we do filtering in general in pandas. Right? Go back to the previous example. Other than doing filtering, we can also do computed fields. Right? For example, previously we have constructed a new sequence of Boolean statements called isWife, which requires both the gender to be female as well as the marriage status to be married. So it turns out that among the 6 observations, we only have the second observation to be true for this isWife value. So we can also make the subset selection by isWife, and we can manually update the column called remarks to wife. So this is something what we can do. Right? So let me slow down and repeat, explaining the process. We first construct a sequence of Boolean statements, which will be true only when the observation is satisfying our criteria. So this is equivalent to what we did in Excel of filtering. After filtering out the observations with the corresponding criteria, we can either do by selecting the subset, alternatively we can do by assigning new values and creating new columns and so on. In this example, previously when we defined the column of remarks, by default we set all the values to be string none. But by making the selection using the Boolean statement of isWife, we can precisely locate on the observations that are wives and only give them those observations a remark called wife. So this will help us to make the proper selections of certain observations that are consistent with certain criteria, then make some updates of the data frame by assigning values and so on. So this will give us only the second observation with the updated value of wife, which is the new remark we just defined. Right? So let's quickly go through the exercise together. Let's run the code together in the Jupyter notebook, and then we see if we have any issues. So to continue our previous exercise, we continue using ilog to make the references. The only difference is that depending on whether you are referring to a single column or a subset of a single column, that will give us slightly different data types. If you are selecting a single column or a single row, it will give you panda series, as we can also check it here, panda series. If you are selecting a subset, although it's also selecting only the second column, but the expression is in the term of a subset, 2, it's as if you are using a bracket of only 2. So instead, it will select a subset of the data frame, which will give us a data type of data frame instead of panda series. As I said before, in most cases, this is not very important. If you realize this is not the data type you want, you can always make the conversion. So we do not usually worry too much about this. Then the remaining exercises are a little bit more straightforward. Once we know how to make the proper references, we can update the values. Before the assignment, the data frame will look something like this. After making the reference and updating the values, the corresponding values will be updated to 0 to 9. Right? Note that the assignment is also element-wise. You assign the number of 9 to 2 elements at the same time. Similarly, you can make a reference using ilog. When using ilog, you only refer to the corresponding indices, integer position, and also you make sure that the stopping point will not be included. So in the end, you are selecting a single row and 2 columns. So both are 0 here. So this is what we have already seen in the slides. Now let's briefly talk about defining a new columns, also by talking about combining data frame with logical expressions. Whenever you are referring to a new column which the name is not currently contained in the existing data frame, Python will help you define a new column at the end of the existing columns. So we are using log because we are calling by the name. We are selecting all the rows and we are calling a new column name called remarks. Then Python will define a new column called remarks, which will have your specified value of none. Right? So this is what we did, how we define a new column. And then we talk about logical expressions by making selections of subset of rows, which is essentially filtering. So let's take a closer look to what this line of code is doing. So data frame gender is a specific column that will give us a sequence of values of males and females, right? The first 2 are females and the last 4 are males. If we use the double equal sign to check individually element-wise whether they are equal to female, we would expect the first 2 to be true and the last 4 to be false. So let's copy paste this part and see. Let me copy paste quickly. So this will give us a list of Boolean statements, 6 of them, true, true, false, 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 false. And we are going to assign this new list of Boolean statements a new name called isFemale. IsFemale. So this is what we have. And later it will be used to do the filtering. Similarly, we can do some other things based on the mathematical or numerical expressions like wage greater than 4 or a combination of multiple criteria. So for example, wage greater than 4 will give us the same, well, a different outcome, but the same shape of a list of Boolean statements. And for this combined operation, let's take a closer look. Gender equal to female will give us the same isFemale, and data frame married itself is a Boolean statement. It's a Boolean statement, so by itself it's a false and true statement. If you combine 2 lists of Boolean statements, we cannot directly use AND because by definition, AND can only be applied to a single pair of 2 Boolean statements. Like, if you still remember, true and false will give us false. But this AND operator can only be applied to a single true and false. If you have 2 lists of true and false, you need to use this AND symbol instead of the AND word. Shift number 7, right? So by doing this, you are doing element-wise AND operations. So this will give us the overall true and false, which is true if and only if both individual elements are true. So for our 6 observations, we require this will be true, which is wife, so that it's female and then it's married. So only our second observation is true. All the others are false. We will end up with a list of Boolean statements called isWife, which will be something like this. After we have the corresponding list of Boolean statements, we can use them as a filtering criteria for us to either to do a selection of a subset or to do some computed fields assignment. So for example, if we are trying to select a subset of only the females, once we define the isFemale, this is what we have already defined before, we can directly put the isFemale into the lock statement by making the reference of only the female observations. So this will give us only the 2 observations who are female. So this is equivalent to what we did in Python of filtering. Similarly, because we have defined this extra new column of remark. So for now, the remarks are all none. Let's see, data frame. The remarks are all none. So what if we want to, for any observations that is a wife, means that it's a female and it's true for married, we are going to change the remark or update the remark to be wife, right? So this is what we have done so far. We define a new sequence of Boolean statements called isWife, which is false, true, false, 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 false. Then we can directly apply, this is the same, we can directly apply this list or sequence of Boolean statements to the rows. In total, we have 6 rows. By default, we are selecting all of them. So by default, all 6 rows are true. But now, instead of all true, we are going to change according to isWife. What is isWife? IsWife is false, true, false, 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 false. So if you understand intuitively, as long as it's false, we are removing that column. We do not select that row. So in the end, we will only select the second row, and we are going to update that second row's remark column to be wife. So as a result, we are only going to select this cell, and we are going to change from none to wife. So let's run the code and see what will be different, right? Like this. So by making the selection itself, we are not changing the original data frame unless you're updating the values. So in other words, we do not remove all the false columns, but we're only referring, not referring to them. Unless you do a self-update, otherwise they will not be removed. We will see more examples like this once we work with larger data sets. But this is more or less, roughly speaking, the syntax or the approach that we use to do either references, filtering, or computed value updates. So these are the fundamental ways that we can modify existing data frames values according to some criteria and conditions. Right. Do we have any questions at this point? If not, let's continue with working with, well, in general, larger data sets. So this would be the second component of descriptive analytics in Python. Well, we have seen some of the examples. Later we will see. We have seen some of the examples back in lecture 1 already. But well, in Python, things are done in general in a different way. So the first thing that we're going to teach is to read data from existing files. So to do that, so before continuing with our slides, let's shift to the new Jupyter workbook called Lecture 09 Descriptive. It's not a lot, and let's try to cover everything by today. If you encounter the previous challenges while importing the certain packages, you're encountering some error message, check one of the 3 installation code on the top. So after we are loading, we are ready to read in any of the data files using the function called read_CSV. This is a function that belongs to the PD package. But the first thing you need to make sure is that your data file is already there. For me, we are trying to load a new CSV file. The CSV file we are quite familiar with already. We deal with the CSV file back in Excel. We say they are comma separated value files. Actually, they can be opened by Excel as well. So the first thing we need to make sure is that the file is already there. If you directly call the file's name, you need to make sure that the files are within the same folder as in the Jupyter notebook. So let me see. Oops, my file is not here. So if you try directly loading the file, error message, because of course the file is not even here. So in the online version, I will have to manually upload the file as well. Let me upload both files. Those are the 2 CSV files we need to work with. Right? Once they are in the same folder, means that they are under the same file directory, then you can directly load them. And this data, which is the new variable you define, will be a new data frame. It will also show you how many rows, how many columns. Basically, that's a much larger version of the data frame that we just worked with, right? But with more than 500 observations. More generally speaking, well, this can be quite challenging because more generally speaking, if you put your data file in a different folder, means you're in a different directory, then you will have to specify the exact location. For example, if it's within a folder, something like this. But by default, let's start from the simplest case where your data file is under the same folder as your Jupyter notebook, then you can directly call the file name. Right? Well, this is the recommended way because we're not managing a very large project with a lot of different data data files and so on. So you can directly put them all under the same folder and directly call the name to load the data set. Right? And if you check the type of the data set, it's data frame. That's the type that we just learned. Now you can quickly try this. This is the first step, so I need to make sure that everyone is able to load the data correctly. If you encounter any difficulty, raise your hand, let me know. Let me try to fix. In the offline version, let me also quickly try this. In the offline version, because I already put them under the same folder, under downloads, so I should also be able to do this. Of course, the visualization package is not installed yet, but that won't affect our pandas. So I should also be able to do this. But in order to make the plots, of course, I need to manually install this library as well. But let's save the time of doing that. Anyone cannot import the package. Sorry, not the package, but the data. We use the function name called read_CSV, and followed by a quote string of file name. Okay, good. Let's continue. So after reading in the data set, it should be automatically converted into a data frame. So the first thing that we want to know about is to have a very first glance of the data. So let me quickly teach you several of the very useful methods. One of the most commonly used methods when you just load a new data set is called head. Well, by the word, you can simply imagine what we do, right? So the word head will print out the first several rows. So for example, if it's head 6, it will print out the first 6 rows of the data set for you to have a quick look. And similarly, we have another method called tail. Head and tail, right? Head is the first several rows, and the tails will be the last several ones. And by default, it's displaying both, but well, in case that you want a closer look. Then we will start talking about some of the descriptive analytics when using pandas data frames. So here, the screenshots I show here are slightly different than what we are going to do in the Jupyter notebook. So let's go to the Jupyter notebook directly, and later you can see. Here in the slides, in the screenshot, that was the version of Python from probably 1 year or 2 years ago. So at that time, it still allows us to directly use data.mean. But the method mean will compute the average value for each column. But we will realize that we can no longer do that directly, unfortunately. But let's do it together in the Jupyter notebook. Let me put it slightly bigger in the online version. So the type of the data is data frame, and this is the very useful method of head, which will give us the first 6 observations, 0, 1, 2, 3, 4, 5. And of course, if you want to take a look at the first 16 or first 100, you can also do this, right? You specify the first several numbers of observations. Instead, if you are not interested in looking at the first several, but the last several, you use a method of tail, head and tail, right? So this was the last several ones. By doing this, you know in total we have 526 observations, right? So this is head and tail to give you the first look of the data set. Then we are ready to compute like the means and the medians, like the summary statistics. In Python, the function to compute average is not called average, like what we did in Excel. It's called mean. The word mean, actually, it's just mean average or mathematical expectation. So if we directly try to compute the mean as what we did in the lecture slides, unfortunately, we will have an error. Why is that? Well, the reason is also very simple. We can only compute the average value for numerical values, right? Like, for example, for the first 3 columns, these are wages, educational years, experience years. Even for the Boolean statements, later we realize we can compute the mean or the average value. But for categorical variables, which are strings, like female and male, well, categorical variables, they are strings, so we cannot directly compute the average value for a string. So that will give us an error. How do we deal with that error? Well, we can use the help function. You do not need to follow me on this. I'm just to show whenever you encounter an issue, help function can be useful, as indicated by the name, right? So we need to type in the full name. The full name will be pd.dataframe, because the object type will be a data frame. You do not have to follow me on this. You can always Google or ask anything else. But here we can use the function, help function. The method is mean. So it will give us documentation to explain how do we use the mean method when applying to a data frame. So let me take a closer look. Right, access, optional. Skip an A, what if your observations has missing values, which we do not. Numeric only, default is false. Whether we should only compute average for numerical values, well, this is what we want. By default, this is false, means that we compute average for everything, which will give us an error. So that's why we need to include numeric only to be true. So we need to type down something like numerical only. I don't need to manually type this because this is already here. Numeric only equal to true. Alternatively, numeric only equal to 1, because 1 and true, they are interchangeable in many cases. So when computing this, after computing this, it will give us the average value for all the numeric columns. So for example, the average hourly wage is around 5.896. Average education in years is around 12 point, and so on. Interestingly, this is a question I already asked when learning about this data set in Python. Here, let me ask again. Interestingly, we can also compute the average value for the Boolean column, which will give us an average value of 0.6 for the marriage status. Can anyone quickly tell me what does it mean? How do we interpret this 0.6 as the average value of marriage status? Don't be shy, you can directly shout it out. I think it's this. And even if you say it wrong, that's fine, right? That's fine. Anyone? Come on. Around 61% of what? Yes. Louder. What? Sample? Of the samples are exactly. So in the slides, we actually have a more straightforward explanation. Whenever we have a Boolean type of variable, it can only take the value of true or false. As we say already in Excel, true is just 1, false is just the 0. What happens if you compute the average value of 0 and 1? So 0 will never contribute to the average value, and 1 will contribute the average value. So by taking the average value of 0 and 1, basically you get the percentage of the observation of 1, in this case, the percentage of merit observations. So roughly speaking, 61% of the observations are merit. So this is how do we interpret the average of a Boolean statement. And of course, what happens to the male and female column? That's a string. We cannot compute the average. So we can also print out the type. The type is a panda series. So this is what we compute, and we compute the output is displayed as a panda series. Similarly, we can also compute the median. Recall that the median is that the middle point where 50% is below and 50% is above, and we still apply the same numerical only output. So the median of wage is slightly slower than the average wage because we know there are many outliers for the very rich people. This is what we have already covered back in Excel. And using the same logic, you can compute the standard deviation as well as the variance for the numerical observations. By numerical, we also include 0, 1, or Boolean statements. And of course, you can measure the maximum as well as the minimum. So here, if you quickly compare, when you are trying to use a maximum argument, you do not need to indicate this numerical only, because by default, the max method can also be applied to strings without any errors. So here, pay attention. The max method is not saying that male is larger than female. Well, that would be politically very incorrect. It's just comparing the alphabets, right? Starts with M is later than start with F. So that's why it's saying, okay, I'm giving you a maximum value in terms of male. To give you a more concrete example, this is my favorite example. I need to mention this. So it is possible to compare the values of two letters, although we should not do this in principle because it usually does not make any sense. If you compare A and C, it will be false because C appears later in the alphabet. So my favorite example is here, right? So if we compare whether CTU is greater than, no offense, CHK, that's true. So we CTU are, I don't know, by Python is better than CHK. But if you want to know the details, it doesn't mean that it's directly according to alphabet. To quickly show you whether if I change it to all uppercases, whether CTU uppercase is greater than CHK, it becomes false. So the comparison actually it's not very meaningful. It's just making some comparison between the Unicodes. So be careful when you are treating strings like numerical values. Usually they do not mean anything, right? And of course, you can measure the maximum value within a specific column. Once you have a single panda series like wage, you can measure the maximum value for that panda series only. And similarly, let me further introduce some other useful, let me quickly go through the rest. Let me quickly introduce some of the other useful methods include value counts. So this method called value underscore counts for any categorical variable that can only take several discrete outcomes, like for our column gender, it can only take female or male. If we want to count how many numbers of males and how many numbers of females, we can use this method called value underscore counts. It will give us a frequency table. Male appears 274 times, female appears for 252 times. If you instead of the absolute number of occurrences, you care about the relative, means you need to specify something like normalize equal to true. You do not have to memorize this, just be able to interpret this. What do we mean by normalize equal to true? Means that we are normalize the whole population, all the observations, to a base of 1, and only care about the percentage of each outcome. So by doing this, we should be able to see the percentage of each gender, which is 52% and 48%. So that's the difference between simply value counts and value counts with normalize equal to 1. And more generally speaking, for descriptive analytics, you can use a more comprehensive method called describe. By doing this describe, it will try to give you pretty much all the fundamental summary statistics. Let's try it. Wage summary. It will give you, of course, by default, for only the numerical values, for the number of observations, which is count, the average value, the standard deviation, the minimum for each of the 4 quantiles, and the maximum. So this is very helpful because by using a single method, we can get a pretty comprehensive understanding of all the numerical columns. And I guarantee you that this is also useful because when I write academic papers, I use a certain data set. I need to report exactly the same data summary statistic in something like this. How many observations, what are the mean, standard deviation, quantiles, and so on, extreme values. So this will be very useful if you want to get an overall understanding of your data set. Then let's quickly go through the slides of what we already covered, and then spend a little time, just a little time, on some of the data visualization techniques that we already learned, but by summarizing a data set. So this is mean, and this is how I explain the mean, the average value of a Boolean statement. What does it represent? Right, the percentage of a positive observation. So similarly, this is median. This is value counts, And if you want to only care about the percentage, you should set normalize equal to true. If you have already forget about what are percentiles and what are quantiles, well, this is the slide that we used back in lecture 1, where we say about summary statistics. For summary statistics, this list, the table contains the majority of the summary statistics that we have. Basically, the 50% quantile is the so-called median. And the 50% percentile is the median, which is also the second quantile. The first and the third quantiles are the 25% and 75% percentile. And sometimes we call them Q1, Q2, and Q3. They will be useful in the box plot. Hopefully you still remember. In the box plot, we plot a box which include the median, which is Q2. The range of the box will be Q1 and Q3, and the length of the box is called the IQR, the interquantile range. And also we would have a Q1 minus 1.5 IQR, Q3 plus 1.5 IQR, which are the common range. Any extreme observations fall out of the range are called outliers and will be visualized individually. So this is something that we already covered in Excel, and we also know how to make the box plots in Excel as well, right? So let me quickly show you how to make a box plot in Python. So it's the same. We use the same package, maxplot library. We call it PLT, and the function is called box plot. You can actually specify whether you want the box plot to be vertical or horizontal, right? So this is quite straightforward. As we say, the wage distribution is heavily asymmetric, means that we have a lot of poor people, but very few, but very extremely rich people. So it turns out we, on the right-hand side, or on the top side, the outlier, we have many outliers who are extremely rich, right? So similarly, we also learned the notion of histogram back in Excel. Note that histogram is similar to a bar plot, but it's actually different in meaning. In a bar plot, the height of the bar represents the corresponding actual values. In a histogram, the height of the bar actually represents the relative frequency, or the number of occurrences in that specific range. So those, like what we have already covered in Excel, if you want to describe the distribution of a single variable, like wage distribution, box plot and histogram are the commonly used tools. Then, if you want to visualize the relationship between a pair of observations, we commonly use a scatter plot like this. So this is a scatter plot. Well, scatter plot is not something new. We just mentioned it in the previous lecture, right? We just use a scatter, but carefully select y and x and y, so horizontal and vertical axis. So here we are making a plot of the hourly wage against the years of education, and overall, the trend is going above. So we make the exact same scatter plot in Excel, if you still remember. And overall, we can have a pretty good conjecture of higher years of education will lead to on average higher wages, which is good news. And finally, we can use the method called CORR, which stands for correlation. We generate the correlation table back in Excel as well. Hopefully you still remember. And here it will generate for all the numerical columns, generates the correlation table. So we say, so this is the basic revisit of the correlation table. Correlation is a value from -1 to 1, which measures the overall tendency of a pair of data series. The closer to 1, the more positively correlated, as in here. We have the correlation between wage and education to be 0.4, which is quite large and positive. So that on average, we would expect that an observation with higher years of education will on average have a higher wage. It's not an absolute statement, but that's overall average conjecture, right? So let's quickly run the code together. We are going pretty fast because either we have covered them in Excel, alternatively we may cover some of them like scatter plots in the previous lecture already. So to make a horizontal box plot, you need to specify VERT equal to false, means VERT means vertical, and if VERT vertical is true, then your box plot is a vertical one, depending on what you want. They are exactly the same, just well in the different directions. Then you can make a histogram. A histogram will count for a pre-specified beings, count within each interval how many observations do we have. So again, let me repeat. We usually use either box plot or histogram to describe the distribution of a single continuous variable. So same as before, here we use the functions from PLT. And we can make a scatter plot. So here, actually, this example is a very good illustration of sometimes why do we need to adjust the alpha value. We just covered in the previous lecture, hopefully you still remember, this alpha value will control the level of transparency. If by default the alpha value is 1, then it's not very clear. For example, you may have 20 points on the top of each other here, but because we have no transparency level, they're all stacked together, so we cannot directly see how many points are there. So in this case, if you manually change the alpha level to a lower value, we were using 0.3, then because the dots are transparent, if they're on top, if they overlap with each other, for example, in this area, the color will be darker so that it will give us a better visualization of the density of the dots. So this looks much nicer and more informative by controlling the level of alpha. And when making the correlation table, of course, in today's version of Python, we need to specifically specify numeric only is true. Otherwise, it will again give us errors because it will only compute the correlations between numerical columns. And of course, any variable correlation with it itself will be 1, so that on the diagonals it's not very interesting. So we can take a look at either the upper triangle or the bottom triangle for the individual pairs of correlations. We explain all of them, right? A 0.4 means a positive correlation between education and wage, and we have a negative correlation between experience and education because usually the more years you spend in school, relatively the less years of your working experience, right? So this is all the familiar topics that we already covered in Excel. So let's use the remaining time, around 10 minutes, to quickly talk about how do we do pre-processing when we're dealing with the missing data. So to do that, let's quickly import a data set called GDP. It contains, let's take a closer look. It contains all the 265 countries and regions of their GDP value from the year of 1960 to the year of, I think the last year is 2021 or something. So this is a very huge table, but as you can imagine, not all the observations are available. For example, in our first country and region, we have Aruba. We find that historically, many years, Aruba's GDP is not observable, means that we do not have the information. So in that case, sometimes we need to rely on some pre-process or data cleaning, right? So after we read in the GDP data frame, we can first, let's go through the slides before we go to the real code. So this is how the data look like. Sometimes in some countries and regions, they do not have the exact GDP observations, so that it appears in the data frame as NaN. It means missing. So we can rely on several very useful data like methods. One of them is called is null, and the opposite is called not null. The word null in English, it means nothing. So is null will help us detect whether a specific selected area contains or it is a missing observation of NaN. So let's see this line of code. So gdp.log, right? By log, we mean we are using the label-based referencing. So we are going to select all the rows and only the 2 columns of GDP of 1960 and 1961. So we are going to apply the method called is null. Then for each individual observation, for that 2 columns of data, we are going to do the element-wise check whether the data is missing. Because the method is called is null, so it will return true only if the observation is missing. So if it's NaN for Aruba, it will be true. For the second country, we have a GDP value, then it will be false. Right? So similarly here, what we do in this similar exercise is again to use the log referencing system. We are going to select a subset. So let's take a closer look of what we do. It is like we are doing a filtering by selecting GDP 1960. That is a column. That column of not null will give us all the individual observations that are not missing. Means that we have certain values. We do not have NaN. By doing this, we are selecting a subset of all the countries and regions with a non-missing GDP value in the year of 1960. Right? So by doing this, we are selecting a subset of the rows and also the subset of the columns. How exactly? For the rows, we are selecting all the observations that are satisfying our criteria, which is for 1960, they are not null. In other words, we are selecting all the observations which has a GDP value for the year of 1960. That's for the row. For the column, it's straightforward. We're only selecting the 2 columns of country name and 1960. So by doing this, we are selecting a subset of the data frame that later we can work with. Right? So this is basically what we learned so far, combining the references and the filtering operations in data frame. Then let's briefly talk about how do we deal with the missing values, depending on what you want, right? For example, if you want to be very restrictive, as long as a country or a region has a missing value, no matter how many missing values, like shown in this example, as long as we have for a country, for any of the year, the GDP value is missing, I'm going to remove that observation. So we call this by the method of drop NA. Formally speaking, it will remove the rows with any missing values. After the drop NA, we need to make assignment. Means that this drop NA does not automatically remove the missing values on the original data frame. In result, we will have a new data frame, a new object, so we will have to give it a name. Here we call it temp. So this temporary data frame will contain all the so-called complete observations. Recall that in Excel, in the Power Data queries, we do this by remove blanks. So this is something similar. This is something similar. So this is drop NA. So this is what I said. The method of drop NA does not automatically remove the missing values from the original data set. So you will need to, so after you try the drop NA and you check the original data frame, GDP subset, the missing values are still there. So in order to keep the results after dropping the NAs, you need to make a new assignment called temp, or whatever name you want. But you need this new assignment. Alternatively, if you do not like this new assignment, I really want to perform this drop NA on the original data frame, there's another option. You can specify in the argument called something like in place equal to true. This in place equal to true means that instead of requiring a new assignment, you will directly remove the missing values, the row with missing values in the original data frame. So in that case, later we will run the code again. In that case, if you double check the original data frame, the original data frame will already update it because the drop NA operation is now in place. It is performed directly on the original data set of GDP subset. Right? So these are some quick introductions of how do you remove rows with missing values. And of course, you instead of removing the rows, which is sounds a little bit restrictive, you're simply removing it. You can choose to do something else by fill in the NAs. So the corresponding method is called fill NA. For example, instead of NaN, which stands for missing, you can manually. It is as if you are finding all the missing places and replace with the missing values by something you define. Here we can replace all the NaNs by unknown. So after fill NA, whatever string you put in or whatever number you put in will be used to replace all the missing values. Here you can use unknown. Alternatively, you can use a 0. For example, if you feel like, okay, if I do not see a GDP, the GDP must be 0, which is not true in general. So be careful when you are filling in the NAs. You need to make sure that you need to understand the fill-ins correctly. Sometimes we do not observe the GDP not because it's nothing, not because the GDP is 0, but because the information is unavailable, it's unknown. So while it is allowed in Python to fill in NAs with 0, you need to think twice before you really do it. The good news is, of course, now you are dealing with a data frame with all numerical values, but the bad news is that this 0 may not be consistent with the reality. Right? So let's use the remaining 1-2 minutes. Let's quickly go through the code together to quickly show you what's the difference between in place and the assignment of drop NA and stuff. So this is null. It will return us a list or data frame of Boolean statements of the corresponding values to be missing or not. So is null will be true only when it is missing, and not null will be the opposite. Similarly, we can use this to select a subset of all the missing values or of all the values that are not missing, depending on whether it's not null or is null that we're using. So we create a subset, a copy of GDP, and let's apply drop NA. After apply the drop NA, we need to make assignment to a new object called temp, or whatever name you want. Then this process is completed. Because if you check the original GDP subset, the missing values are still there. In other words, this drop NA are not automatically conducted on the original data set, which we call this in place. If you really want to do it in place, you need to write down something like in place equal to true. By doing this, any new assignment will be meaningless, will be useless, but the original data will be updated to a version that does not contain any missing values. Right? So similarly, you can apply the method called fill NA, which will replace all the missing values by the value that you specify. Similarly to the drop NA, you can also specify whether you use an in place. If the in place is true, you do not need an actual assignment. If the in place is false, which is by default, you will need an actual assignment for the change to take effect. So that's roughly speaking the way that we're dealing with missing values. So that's more or less lecture 9. Towards the end, I'm going a little bit too fast, but it's already 53, so I'm a little bit over time. Apologize for that. Well, that's more or less it. And next week, I believe Prof. Zhang will be back teaching the session, and I will see you, well, during the fun exam. Some of you, at least. Questions, just talk to me outside.